Hello class, welcome to the part 4 and the last one of this subtopic 3.8, solution to trigonometric equations. And today guys, I'm going to explain to you how to convert trigonometric equations into normal quadratic equations when that's necessary. Let me tell you what I'm talking about. For example, try to remember when we dealt with this type of equations. For example, when we had exponential equations like this, we already worked with these types of equations. And if you remember, what we did in here was a relabeling, or basically a change of variable. In here, my variable is x, that's understood. And this seems to be a complicated equation. But when we do this relabeling, when we say let's create a variable y and let's make it equal to e to the x, then what we can see is that if we elevate to the square both sides, we get this, right? And thus you get this, e to the x to the square, that's going to be e to the 2x, which, if you notice, this appears over here. So basically, with this little relabeling, by saying let me create another variable y and let's make it equal to e to the x, then I can transform my equation into the following: e to the 2x, which is y squared, plus e to the x, which is y, minus 6 equals 0. And I have transformed this equation, which looked very complicated, into this equation which is more manageable and which we know how to solve. Then we solve this equation, we get two values for y equals something or y equals something else, and then we go back to this place, right? Because y is supposed to be equal to e to the x. So basically this can be converted again into e to the x equals this value, or e to the x equals this other value, and basically we are done. We take the natural logarithm from both sides and we are finished. Okay, the same thing we had already done before, guys, we're gonna do in here. So this is a very general process, or a very general tool, or no, it's not a tool, it's more like a method. And we're going to apply this same method for trigonometric equations, and you're going to see how it works out. So let's get started. We have this equation y, guys. Cosine of 2x equals sine of x. By the way, I'm going to make several changes in here. For example, I'm no longer going to call the variable theta. I'm going to call it x, just so that you understand that there is nothing particularly interesting about theta. When you talk about trigonometric equations, you can call the variable anything you want, it doesn't matter. So let's work with x in here. And now I'm giving the interval in again in a different way, because we have usually been working with this symbology. Can you remember? Okay, well, but this is basically the same. All right, what this is telling me is that x should be greater than 0 and less or equal than 3 pi. So basically, if you want to rewrite this in this type of notation, it would look like this: x must be in the interval from 0 to 3 pi, excluding 0. That's why you don't have the equal sign here. Can you see? You just have the less, yeah. And 3 pi, including 3 pi. That's why you have the equals part in here. So basically, this and this are completely equivalent, guys. They mean the same thing. It's an interval going from 0 to 3 pi, excluding 0 and including 3 pi. And the third different thing, guys, that you must be noticing by now is that I'm including in here something that I haven't included in the previous exercises. I'm including an interval that goes outside 0 and 2 pi, because the previous intervals were something like from 0 to 2 pi, or from 0 to pi, or from pi over 2 to 2 pi. We were always working within 0 and 2 pi, always working within these numbers. And now I'm going up to 3 pi. So what's up with that? Okay, you're gonna see in a moment how this works. So let's get started. Okay, so we have cosine of 2x equals sine of x. There is no direct method to solve these equations, but since I'm telling you right now that we should create a quadratic equation out of this, you must get the feeling that somehow we must have the squares of the trigonometric functions in here somehow. So let's go to our page of formulae. And if you notice, guys, we have in here cosine of 2x, which is what we have in here, cosine of 2 theta. Remember, the variable is not important. And I look at all the possible equivalences for this identity, and I'm gonna decide for this one, guys. 1 minus 2 sine squared of theta. Why am I deciding for this one? Because this is the only one that has also sine. Okay, because for example, look at this at this one, it has cosine and sine. This one has cosine, right? And this one has only sine. And why do I want this one? Because if I choose it, let me choose it right away, and let me substitute it. You're gonna get 1 minus 2 times sine squared of x equals sine of x. By using that particular substitution, guys, we can see that we have the function sine, only the function sine, and we have its square, the square of sine, and then we just have sine, and then we have a constant term. So this gives me the feeling that in the end, let me throw all the terms to the left. Like this. Then let me multiply by minus 1 and rearrange a little bit the terms so that it looks nicer. I'm multiplying by minus 1 both sides and rearranging a little bit. So this is what you're gonna get. There you go. Try to make sure of that. Okay, so by using this special identity, guys, that this is equal to all of this, I can come up with this equation. By using any of the other, for example, you could have used this one, the one in the middle, the third one. You're not gonna be able to come to something like this, which is a quadratic equation in sine of x. What that means is that you have sine to the square, and then you just have sine, and then you have another term which is constant. This is what is known as a quadratic equation in sine of x. And it is at this point that you make the change, the relabeling. Okay, what you do is this. Okay, I have a trigonometric function to the square, and then the trigonometric function alone, or well, not alone, raised to the first power, and then a constant term, and you may try to do a relabeling, also known as a change of variable. And I'm gonna say, all right, let me create the variable y and let me make it equal to sine of x. With this change, then y squared is equal to sine squared of x. By raising both sides to the square, that's what you get. And then you can see that in here we have y, and in here we have y squared. And let's make that change already. So therefore, with this small relabeling, we can write this equation now as this: 2 sine squared of x, which is y squared, plus sine of x, which is y minus 1. And basically, we have reduced the complexity of this equation into a quadratic equation, which seems simple to solve. So let's try to solve this equation now. You have 2y squared plus y minus 1 equals 0. Let's try to solve by factorization if we can. We have 2y, y, and then we have, in here must be plus 1, and in here could be minus 1. Is it gonna work? Yes. Make sure that this is the factorization of this expression, guys. Please make sure. Pause the video and make sure. Okay, so basically we have a product being equal to 0, and that means that either the first factor is equal to 0 or the second factor must be equal to 0. And what this means in return is that 2y equals 1, and then y equals 1/2, right? Or y equals minus 1. Okay, perfect. So we have solved this equation, guys. We already know the value for y, which is this, and the value and the other value for y, which is this. But remember, y is not the variable that we're working with. The variable that we're working with is x, and x is inside these trigonometric functions. So we need to go back. Now that we have solved for y, we need to go back to this, to remembering that y is in fact sine of x. So then I have that y, which is sine of x, must be equal to 1/2, or y, which is equal to sine of x, must be equal to minus 1. So we have two branches. We have this branch to deal with and this other branch to deal with. And I'm going to do it separately, as always. So for what angle do I have that the sine of that angle is equal to 1/2? 1/2. So let's see. I inspect the y coordinates. This is 1/2 for pi over 6, and this is 1/2 for 5 pi over 6. So let's write that down. Pi over 6. Then we have that x must be equal to pi over 6, or x must be equal to 5 pi over 6. And for what value do I have that sine of x is equal, for what x do I have that sine of x equals minus 1? Well, for 3 pi over 2. Okay. Now this is pretty much the way we have done it in the previous exercises, right? We just go to this image, guys, which covers all the angles from 0 to 2 pi, because remember that 2 pi is one full turn, and pretty much you can think of 2 pi being on top of 0. And that's it, right? It seems as though we are done. Okay. Now, the problem, well, not the problem, the thing that I haven't told you guys is that there are many more solutions to this equation, not just pi over 6. For example, if you just consider sine of x equals 1/2, x equals pi over 6, and x equals 5 pi over 6 are not the only solutions. You get more solutions outside of this interval, okay, for numbers less than 0 and for numbers greater than 2 pi. Okay, for example, I like you to take your calculator and put it in radians and then do this. Try to input into this equation, try to write, I mean, if you write sine of pi over 6, remember, you need to put your calculator in radians. If you put this value, of course, you will get 1/2. That's clear, right? We have solved this equation. But also, if you write this, sine of pi over 6 plus 2 pi. if you input this value, guys, which is another angle, it's pi over 6 plus 2 pi radians. It's another angle different from pi over 6. You will get the same result, 1/2. The same goes for 5 pi over 6. If you input sine of 5 pi over 6, you will get 1/2. But also, if you write, for example, 5 pi over 6 plus plus 2 pi, you will get the same. Now, why is this, guys? Why is this? This is due to the periodic nature of sine. Remember that the trigonometric functions, sine, cosine, and tangent, are periodic and they repeat themselves. If you want me to convince you, let's go back to Desmos. Let me write the function f of x equals sine of x. And let me check for what values do I have a value, for what values of the angle x I have a value of the function equal to 1/2, which is what we have in here, right? For what value of the variable x do I have that sine of x equals 1/2? So 1/2, I mean, this is 2, therefore this is 1, and therefore this is 1/2. So we have 1/2 in here. For what value? For 0.5. For 0.5, right there. For, well, but that's not. I mean, what did we get in here? Pi over 6, which is in this. Let me see if I can put this in radians, guys. Let's write in radians. Okay. So, okay, try to right there. Can you see for x equals 0.53, we get a y of 0.5, which is 1/2. So try to look at the value 0.53 and copy that value, please. 0.53. So that's the first solution, guys. That's pi over 6. If you calculate pi over 6 in your calculator, you will get pretty much that. Calculate this thing in your calculator. You will get 0.52. You see, so that's the first solution. That's this one. That's right here. 0.50. It's difficult. Okay, it's that value pretty much. Okay, and then the other value is 5 pi over 6, which if you put in your calculator, you're gonna get 5 pi over 6, which is 2.61. So for an x of 2.61, let me write that in here, which is close to 2.61. For this value, we should also have that sine of this value is 1/2. So let's see. This is 1/2 again. No, I'm sorry, this is 1/2 again. And as you can, this is difficult. As you can see, we get 2.63 approximately. So you see the idea, right? But these are not the only values. This and these are not the only values for which you get a value for the function of 1/2. You also get it for this one, and for so many others, right? So it's always repeating. So basically, you have an infinite amount of possible solutions, an infinite amount. All of those distance from one another by 2 pi. Okay, so basically what I'm telling you is that this is a solution to this equation. That's perfect. But any other value of x, guys, any other value of x that is 2 pi, that it has a distance of 2 pi from any other solution will also work. That's why this value also works. That's why this other value will also work. For example, sine of pi over 6 plus 4 pi, this will also work. Why? Because this is at a distance of 2 pi from this one, right? If you add 2 pi to this solution, you will get this. And if you put this in your calculator, and I encourage you to do it, sine of pi over 6 plus 4 pi, you will get also 1/2. Remember to put your calculator in radians in order to do this. Otherwise, it's not going to work. So basically, guys, what I'm telling you is this. This is like the simplest solution, but also you get many more solutions by doing this, by adding plus or actually subtracting, which is the same but in the other direction, subtracting or adding this value, 2n pi, for n an integer. What that means is that n can be either 1, 2, 3, 4, etc. Why 2n pi? Because basically when I give n the value of 1, then I'd be either adding or subtracting 2 pi. When I give the value of 2 to the n, I'm going to be adding or subtracting 4 pi. And so basically it's all of these guys accounts for the multiples of 2 pi. So in here you get 2 pi, 4 pi, 6 pi, 8 pi, etc. And also you go backwards. You can have minus 2 pi, minus 4 pi, etc. And all of which are going to be solutions of this equation. That's how it works. I didn't want to erase that. Okay, so this is the more general solution, guys. And the same goes for this. The same goes for any other solution. So you will get 5 pi over 6 plus minus 2n pi, n being an integer. This is a general solution also of this equation. And for this, the general solution is 3 pi over 2 plus minus 2n pi, when n is a natural number. So this is the general solution. Okay, now for this equation, I'm working over what interval? Now basically we're done, okay? And I know that this has been too long, but let's see, we're not done yet. We're working over the interval from 0 to 3 pi. So basically, let me write the final answers in yellow. So x equals pi over 6. That's one of the solutions. Okay, it's like the primitive solution. And let's see if by adding 2 pi we have another solution inside this interval. The answer is going to be yes. You're going to get x equals pi over 6 and x equals pi over 6 plus 2 pi. Okay, that's going to be inside this this solution. Why am I telling you this? Because of the following. Let me make a little pause right here.